My name is Yu Ming. I'm a PhD candidate at National University of Singapore. Today, I'm very happy to talk about our work, fairness analysis for blockchain incentives. This is a joint work with Tang Jing, Qian Hao, Andrew, and Jian Liang from Hong Kong Baptist University. In this presentation, I will first introduce you a 10-year debate in cryptocurrency community about fairness of proof of stake. This question motivates our study. Then I will show you the underlying incentive design of 4 blockchain systems. After that, we analyze the fairness of 4 designs and verify our analysis by experiments. Finally, we conclude the new knowledge we learned from this study. Permissionless blockchains, such as Bitcoin, rely on decentralized governance. The miner competes some type of resource to maintain the ledger and win network incentives. As example, the Bitcoin. This competition brings striking energy consumption. Currently, only the Bitcoin network itself consumes 129 terawatts-hour electricity per year. It consumes 10 times more than the total electricity consumption of Google, the biggest technology company on the earth. It is also surpasses Norway, a country with 5 million of population, and getting very close to the consumption of New York State. More seriously, prediction says if Bitcoin price continues to grow to $1 million per coin, it may become the second biggest energy user on the earth and getting very close to China, the country with the largest population in the world. That means energy consumption is very important and urgent issue. To tackle this issue, proof of stake was invented. Instead of competing computational power, proof of stake miners compete their cryptocurrency wealth. That means proof of work uses computational power to mine coins, but proof of stake uses coins to mine more coins. Therefore, proof of stake does not require that much energy. It is functioning very well, even with very limited hardwares and electricity. Despite young age of POS, it is now the second popular consensus algorithm. More than 300 POS coins are now trading on the market. However, critics claim that in proof of stake, the rich miner would have more reward and further increase their potential income in the future. And they believe POS obeys the original ideal of decentralization. The other side, POS supporters argue that POS systems are similar to proof-of-work blockchains in design. Thus, they believe proof of stake is as fair as other blockchain systems, such as Bitcoin. Such a debate never stopped since the birth of proof of stake. Besides political concern, fairness also relates to security of ledger systems. If a blockchain incentive is unfair by design, some serious consequences will happen. As example, unfair incentive design may encourage mining pools. Miners may aggregate their power for a higher profit, so the network will gradually become centralized. The centralization may further make the system vulnerable to double spending or transaction rollbacks. Besides, large pools may control the voting of on-chain proposals and chooses the proposal for their own good and satisfy the fairness of the whole. Very recently, in August 2020, which is a few months before, transactions in Ethereum Classic were rolled back due to 51% attack, resulting in $5.6 million of loss. In this paper, we're focusing on the fairness analysis of blockchain incentives. We're trying to answer this question and find some practical solutions. To answer this question, we first define 2 types of fairness. The expectational fairness means that the expected value or the expected income of miners equals to the proportion of his resource. The epsilon delta fairness or robust fairness says that the income of a miner concentrates to its resource with high probability. The first definition, expectational fairness, is easy to understand. As for the second definition, here is an example. Let's say Alice and Bob have two kinds of incentive designs in the game. For Alice, she wins $20 for 100% probability. But for Bob, we reward him nothing with 80% probability, or provide $100 incentives with 20% probability. Obviously, both Alice and Bob will take $20 in expectation, but the reward of Bob is more uncertain. That means Alice feels more fair than Bob in terms of robustness. Now we're ready to analyze the incentive design of real blockchain systems. We focus on proof of work and variants of POS protocol. Specifically, we study Ethereum as a representative of proof of work. Considering there are several variants POS implementations, we select Quantum, Ethereum 2.0, and NXT as representatives of POS protocols. Ethereum is the first decentralized blockchain with smart contract functionality. Currently, it is the second biggest cryptocurrency in terms of market cap. Ethereum chooses proposer by solving cryptography puzzle like Bitcoin. If a miner controls more hash power, he is more likely to propose a block. Therefore, the total profit of a miner comes from an independent and identical distributed sampling, and the profit follows a binomial distribution. Then, we show the incentive design of Ethereum satisfies both types of fairness as long as the miner can play the game for a long time. Besides, the rich miner may feel more fair than poor miners since they may feel fair faster than poor miners. Quantum blockchain is one of the most popular POS protocols. It ranks around 60th among all cryptocurrencies. The consensus algorithm of Quantum simulates that of proof of work. Specifically, the miner uses timestamp to solve a cryptography puzzle. If a miner has more stake, he's more likely to solve this puzzle using a single timestamp. Every second, the miner can check this puzzle using current timestamp, and the first miner who solved this puzzle will be rewarded. The mining process of Quantum is different to that of proof of work, since the profit is a stochastic process. As example, if miner A wins a block, he will win some reward in the block so that he will be more likely to mine in the following blocks. Oppositely, if he loses a block, the new coins will dilute his competition, and he will be even less likely to win in the future. This process is actually a polyarm process. Although the incentive of Quantum is fair in expectation, the mining profit outcomes is much more uncertain. We show that a miner can feel more fair either if he is richer, or he plays the mining games longer, or the reward in each block is smaller. Ethereum 2.0 is another upcoming version of Ethereum client. In this version, Ethereum abandons proof of work and applies POS instead. Specifically, Ethereum has the following features that differs from other POS implementations. First, Ethereum 2.0 uses sharding. So there will be multiple proposers in each block. Besides, the network also provides inflation reward for everyone who possesses Ether in their wallet. We show that Ethereum 2.0 is fair in expectation, like other POS protocols. and the profit outcome may not concentrate to the expected value with high probability. But it's worth mentioning that Ethereum 2.0 can be more fair than quantum protocol since the sharding and the inflation reward reduce mining uncertainty. Specifically, if more shards in each block and the system provides more inflation reward, the miner will feel more fair. NXT is the last protocol we analyzed in this work. It was the most popular POS protocol in 2013. To propose a block, each miner will be assigned a waiting time using the following equation. After that, the miner have to wait time second until the block becomes valid. The first one who submit a valid block wins the incentives. We show that the probability that a miner can win a block, in fact, does not equals to the stake he has. In particular, if a miner controls more than half of stacking power, his winning probability is greater than his power. Oppositely, if he is poor, he is even less likely to win. An interesting question is, what is the stationary distribution of wealth for NXT miners? We find that if a miner is rich, his advantages will accumulate among the mining process. Oppositely, if he is poor, his disadvantages will accumulate. We show that if the miners keep playing this game repeatedly with unlimited rounds, the wealth of miner will finally converge to 0 or 1 with probability 1. As example, if a miner has 30% wealth initially in the mining game, his wealth will gradually dilute it, and finally, he will lose his share. Or conversely, if a miner controls 60 or 70% wealth, his wealth will increase until he controls everything. Therefore, NXT protocol does not satisfy any type of fairness. And more importantly, no matter the initial wealth distribution, the miner either loses his wealth in the mining process or he takes all of the money. We felt very surprised and can hardly believe it. That's why we need experiments to prove the theory. We conduct experiments and simulations on aforementioned systems. These figures shows the profit of a miner along with the number of blocks. Here, the blue shadow represents simulations and the green bar shows system experiments. We can see that the system experiments, in fact, overlaps with simulations. So they verify our theoretical analysis. To compare the system, proof of work satisfies both types of fairness, and the variance of POS achieves expectational fairness but not robust fairness in general. In particular, NXT is not fair under any type of definitions. Currently, there are more than 300 cryptocurrencies using proof of stake and its variants. So how fair are they? We compare the POS blockchains inside the top 50 ranks in terms of market cap. NEO applies a dual token proof of stake model that differs from classical POS implementations. Miners deposit NEO token as stakes and compete to win another token named NEO Gas. This model, in fact, is very similar to proof of work incentive. Thus, NEO protocol achieves both types of fairness like proof of work. Algorand currently ranks at 40th among all cryptocurrencies. It provides only inflation reward and no proposal reward. Thus, this protocol is obviously fair and have no mining uncertainty. However, this mechanism may discourage miners since no proposal reward provided. EOS was the most popular delegate POS cryptocurrency in 2013. It has fairness issue like NXT, since the proposal reward is a constant for every delegates, regardless of their wealth. Another interesting question is how to improve fairness of incentives. We further propose some treatment on both NXT and quantum based on our theoretical analysis. First, the monopolization in NXT is caused by an unfair time function. Therefore, we refine the time function using probability and ensure the proposal selection is fair in each block. The figure shows the incentives of an NXT protocol after refinement, and now it can be fair in expectation. The next step, how could we reduce the mining uncertainty through mechanism design? We propose two treatments that help reducing such uncertainty. One of the solution is adjusting block reward. The system may reduce the reward in each block and at the same time propose new blocks more frequently. Then the system is more likely to be fair. The other solution is withholding block periodically. As an example, the system withhold the reward of new blocks and release them every 100 blocks. As a result, every time the system releases blocks, the reward obtained by miner approximates to the power of them, and the system is more likely to be fair. The figure compares NXT client with expectation refinement and with withholding treatment. We can see that NXT with withholding performs much better. Finally, what else we can learn from this work? Besides computation resource, in fact, POS and POW differ in many respects. The mining process of proof of work is IID sampling, but proof of stake, the mining process is a stochastic process. For proof of work, the mining profit is less uncertain, but the more uncertainty in POS minings. And more importantly, if the incentive design is not fair, or there exists an attacker in the network, the disadvantage or advantage in proof of work is independent to the mining process. And thus, the advantage and disadvantage is a constant. However, such advantages may accumulate in POS. Even worse, the attacker may finally manipulate the network if he attacks the network for a long time. To conclude our paper, we made the following contributions. We defined two types of fairness, the expectational fairness and robust fairness. Based on these two definitions, we analyzed the fairness of proof of work and 3 proof of stake variants. After that, we discussed how to improve fairness using practical treatments. Considering there are hundreds of new protocols are invented, we analyzed the fairness of more protocols. And finally, we discussed the practicality of fairness, why it is important to data reliability and integrity, how it prevents mining pools, and the inspirations for security. That's everything in my talk. Thank you for your interest.